Hey everybody, I'm going to go through the first final exam review. I've titled it Unit 1 Review, and it covers questions from Chapter 2, which was Unit 1. And like I said on the announcement this morning, the these questions on the review were written by the department who was also going to be giving the final exam. So they're very similar in wording and in rigor and type of question that you may see on the final exam. So, question 1, this is from the very first section that we did at the beginning of the semester, section 2.1, finding the difference quotient. I've given two examples here. One is a linear function. Part B is a quadratic function. And the difference quotient is here. It won't need to be memorized. It'll be embedded in the problem if it's something you're expected to do. So what we need to figure out then is f of x plus h is -2. Instead of -2x, I'm going to write -2 times x plus h plus 5. So now when we write the difference quotient, h in the denominator, f of x plus h gets replaced with this. So we have -2 times x plus h plus 5. Now I've got to subtract the whole entire function f of x. So I'm going to subtract the original function in a set of parentheses. The original function was -2x plus 5. So now when we simplify, over here when we distribute, I'm going to get -2x minus 2h plus 5. And then when you distribute here, you're going to get plus 2x minus 5. And that's all over h. And then we have some like terms that cancel, so negative and positive 2x, and then positive and -5. So we have -2h divided by h. H's cancel. So the difference quotient for question 1a is -2. Part B, very similar. I'm going to start by evaluating f of x plus h. So the function itself was x squared minus 2, so rather than x squared, it's input squared minus 2. Now the input is x plus h. I'm going to go ahead and simplify that. X plus h quantity squared is x squared plus 2xh plus h squared minus 2. So that's f of x plus h. That's what goes now for our difference quotient here in the top left. That's f of x plus h right there. So we're going to have x squared plus 2xh plus h squared minus 2. That's this part of difference quotient right there, f of x plus h. Now we've got to subtract the original function f of x, and again, when you're subtracting an expression or a function, do it in parentheses. So we're going to subtract x squared minus 2. So we have x squared plus 2xh plus h squared minus 2, and then when you distribute there, we're going to have minus x squared plus 2. Now the x squareds would cancel, minus 2, positive 2 would cancel. So then we have 2xh plus h divided by h. If we factor out an h from the numerator, actually that should be an h squared right there. There we go. Apologize, but that should be an h squared, this term, which makes that an h squared. Okay, so now we have 2x plus h divided by h. So the difference quotient for 1b is 2x plus h. Okay, question 2 is later on in chapter 2, transformations of functions. It is really based on on how well you remember what parent functions look like. For example, the square root of x originates at 0, 0 and comes over like that. So for 2a then, the transformations are what need to be identified. So the -1 moves the graph down 1 unit. The +3 here moves the graph to the left 3 units. And that minus sign in front is a vertical reflection, so it flips the graph upside down. So the middle point right there of 0, 0 is going to move 3 to the left. Then it's going to go down 1. And then we have that vertical reflection. So rather than coming up and to the right like that, this minus sign is going to have it come down and go like that. But to give it a little bit more exact shape, I'm going to put the original point in there, and it's -3, comma -1. I want to find out where the graph is here at -2 when x equals -2. I want to figure out where the graph is when x equals -1. I'm going to plug in a couple of additional points there. So -2 for x right there. We get -2 plus 3, which is 1. Square root of 1 is 1. And then multiply that by -1, so you get -1. And then -1 subtract 1 is -2. So -2 comma -2. Now if I plug in a -1 for x, I get -1 plus 3, which is 2. And then the square root of 2 is about 1.4. And then -1.4 because of the negative right there. And then -1.4 subtract 1 is -2.4. Right about there. So for part B, the parent function that we're dealing with is an x squared graph, and we all know that's a parabola. This vertex is at the origin right here. So we need to figure out the transformations. We have a vertical transformation up 3 units. We have horizontal transformation to the right. So it's going up 3, to the right 4. And then we have a compression. It's outside the function, so it's vertical. It's a vertical compression by a factor of 2. So following the transformations, going right 4, then up 3, there's my vertex. And as we did with part A, I'm going to get a couple more points to get a more exact picture. And that this will be required for these graphs. I need to have 3 points. Like on part A, I graphed the 3 points here. If this were a test question, I would need to see 3 points total for these. So we've got the point of the vertex 4, 3. If I plug in a 3 for x, then 3 minus 4 is -1. -1 squared is 1. And then 1 times 1/2 is 1/2. And then 1/2 plus 3 is 3.5. So 3, 3.5. And then just because of symmetry, I'm going to have 5, 3.5. So the 1/2 as a vertical compression makes the parabola appear to open up a little bit wider. Okay, part C, the parent function here is the absolute value of x, which is our V-shaped graph with the vertex at 0, 0. And so following the transformations, we're going to go down 4 units, to the left 3 units. We've got a vertical stretch of 3, and then a vertical reflection. So going to the left 2 and down 4, right there. So I know one point is -2, -4. If I want to plug in a -1 for x, right there, the -1 plus 2 is 1. Absolute value of 1 is 1. 1 times -3 is -3. -3 minus 4 is -7. So -1, -7. Right about here. And then that graph's also symmetric. So -3, -7 is on the graph. So for this function, it has been vertically stretched, which makes the graph appear skinnier. Now for part D, the parent function here is what was called the reciprocal function, and this was in section 2.2 is when it was introduced, and then we did transformations of those parent functions later on, I believe in 2.6. But the parent graph of the reciprocal function 1 over x has a vertical asymptote at 0, a horizontal asymptote at 0, a piece of the graph here with a point of 1, 1, and a piece of the graph here with a point of -1, -1. So everything's going to be moved and translated based on the following transformation. So we've got a -3, which is outside the function, so that's going to move it down 3 units as a vertical transformation. We have a +2 there, which is inside the function, so that's going to move it to the left 2 units. So our vertical asymptote is going to be moved to the left to -2. The horizontal asymptote is going to move down 3 units. And then we have a point there and a point here. That would be sufficient for that graph. Okay, question 3 is also testing on transformations of functions. What I'd recommend for something like this, given this original graph, make a table of values for f of x. So we have x and f of x. Identify some key points on the graph. Like those 4 points. So we have -1, 2, 3, -3, -2. Looks like we have 1, 2. We have, sorry, -1, 2 rather. Here we have the point 1, 0. And here we have the point 5, 2. So for part A, we have these transformations, 2 times f of x plus 1. So all of the y values, because f of x is the same thing as y, all of the y values are going to be multiplied by 2 and then add 1. Nothing's happening to the x values though. So what I'd recommend is making a new table of values for each piece with the appropriate transformation. So this one, 2 times y, and then you add 1 to that value, and that's affecting the y values of the original function. So the x values are going to stay the same. The y values are going to double and then add 1 to them. So the y values would become, for that first one, -2 doubled is -4, and then if you add 1, you get -3. The other one you get, for this one, you get 2 times 2, which is 4. 4 plus 1 is 5. For this one, we have 0 times 2, which is 0. 0 plus 1 is 1. That one, 2 doubled is 4, and then 4 plus 1 is 5. Now we have points we can plot. -3, -3, -1, 5, 1, 1, and 5, 5. So just comparing, I know this graph isn't on the same scale as that graph, but what should look like has happened is the graph's been stretched vertically and then shifted up 1 unit. Now for part B, we have this transformation, which is affecting x divided by 2, but then we have this transformation, the opposite of f, and since it's outside the function, that's affecting the y values, and we're just taking the opposite of the y values. So if we make a table of values for this one, we have the opposite of all the original y values. And then we have a transformation there, x divided by 2. And if you remember when we talked about this way back in chapter 2, anything inside the function is opposite. Anything inside the function affecting x is opposite. If it says x divided by 2, you do the exact opposite and multiply x by 2. So all the x values are going to be multiplied by 2 from the original function. So now we have a couple of points to plot. So -6, -2, -2, -2, 2, 0, and 10, 2. Actually, you know what? This should be opposite of that one. So that should be -2. Okay, 10, -2. There we go. That's why that wasn't working. 10, -2 would be about right here. So what, if we were to describe what's happened with this shape, we'd say it's been reflected vertically, so it's upside down, and it's been stretched horizontally, which is what this transformation is. That's a horizontal stretch. Okay, for part C, we are taking the opposite of all the x values. So that becomes +3, +1, -1, -5. And then that's outside the function, 1/2 of f of x. Anything outside the function affects the y values, and it's not the opposite. You do exactly what it says if it's outside the function. So I'm going to take 1/2 of all the y values. -1, +1, 0, +1. So what this is right here is a horizontal reflection, so it's reflecting horizontally. about the y-axis. And then this 1/2 times f of x is a vertical compression, so it's being smashed or compressed vertically. We have 3 comma negative 1, 1 comma 1, negative 1 comma 0, and negative 5 comma negative 1. Or sorry, comma positive 1. Like that. So describing what's happened here, it's a horizontal reflection combined with a vertical compression. All right, question 4, finding inverses. This was from the end of chapter 2, section 2.8, I believe. 2.7 or 2.8, but it's finding the inverse. And the implication of it being one-to-one, one-to-one functions means that its inverse is also a function. So there's 2 steps for finding an inverse, if you remember. The first step is to switch the place of x and y. So x equals negative 5y plus 4. And I'm just replacing all the f of x with y. You switch the place of x and y. And then you solve for y. This is the second step. Second step, solve for y. So you subtract 4 on both sides, then divide by negative 5. And then finally, the notation for inverse of f is that notation right there. So the inverse of f is x minus 4 divided by negative 5. It's the same regardless of the type of function. We have a cubic function here, but it's the same steps. So I'm going to go ahead and just say, okay, that's y instead of f of x. First step is to switch the place of x and y, and then solve for y. So subtract 2, divide by 4, and then cube root both sides. So the inverse of f is cube root of x minus 2 divided by 4. So for part C, switch the place of x and y. Now we have a fraction, and solving equations with fractions isn't what most people like to do, so you can clear the fraction by multiplying both sides by the denominator. So now we have negative y plus 2 times x equals 5, and now we got to solve for y. So one way you could do this is distribute. Then you could factor out, well, then you would want to move the 2x over. So I'm going to say negative yx equals 5 minus 2x. And then you could divide by the opposite of x. So then y equals 5 minus 2x divided by the opposite of x. So it would be the inverse of f for that one. Part D, we switch the place of x and y. The difference here is we have y show up in 2 different places now. We have y minus 5 divided by y plus 1. So we do the same thing. We're going to multiply both sides by the denominator. Clear the fraction. And at the same time, I'm going to go ahead and distribute that x. Now I want all the terms that have a y on the same side. So I'm going to move this term over here and then move that x term over there. So what I would have at this point is xy subtract y equals negative x minus 5. Now from that side, the left side, I can factor out a y. And now I can divide by x minus 1. So the inverse is negative x minus 5 divided by x minus 1. So the biggest thing to remember there for finding inverses are the two steps. Replace or switch the place of x and y, and then solve for y. Okay, question 5. The graph of a few functions here are given. Determine if it has an inverse. So what this question is asking, determine if it has an inverse. What they're asking is the function 1 to 1? If it is, then sketch the inverse. 1 to 1, the test to determine if a function is 1 to 1 is called the horizontal line test. So this one, for example, if we want to call it part A, this graph passes the horizontal line test. So it is 1 to 1, which means it has an inverse that's a function. Part B here, this function does not pass the horizontal line test. So it is still a function, but it is not 1 to 1. So this one is not 1 to 1. So we're not going to find the inverse of that one because it would not be a function. The rest of them are all 1 to 1. Part C here passes the horizontal line test, so it's 1 to 1. Part D as well. So what I would recommend graphically to find an inverse, it's actually easier to find the inverse of a graph than it is of the equation of a function. The same rule still applies. You need to switch the place of x and y. So I would identify some points on the graph. Like this one is negative 2, comma 1, 0, comma 2. Actually, the scale of that looks like they scaled it. So this is negative 2 over here. I didn't see that. So this is actually negative 1, comma 0.5. This is 0, comma 1. This is 1, comma 2. And that's 2, comma 4. So when you find the inverse, you switch the place of x and y. This point, for example, let me get a different color. This point here would become the point 4, comma 2. Which would be about right here. This point would be the point, if you switch x and y, would be the point 2, comma 1. This point would be the point 1, comma 0. And then finally that point would be the point 0.5, comma negative 1. And as far as symmetry goes between an original function and its inverse, they're symmetric across this line right here, the line y equals x. That's one way you can visually see if you have the correct inverse drawn, is if it's a reflection across that line. So we'll do the same thing here. Identify some points. So we have 0, 0. Looks like the scale of this one is normal scale. So 1, 2, 3, 4. This is the point -4, 3. Here we have -2, 2, 0, 0, 1, -1, 4, -2. So to find the inverse of all those, we switch the place of x and y. So this point becomes the point -2, 4. This point here becomes the point -1, 1. Then we have 0, 0. Then we have 2, -2 from right here. And then this point is, switch the place of x, y, we get 3, -4. And then we got to figure out what this is going to look like transformed. So looks like it would come here and there. And then we can just verify that it's a reflection across that line right there, the line y equals x. And just looking at that now, let's see. I think I need to fix that a little bit. Okay. All right, for part D here, we have a point there that's -3, -3. Point here that's -1, 1, 1, 2, and 4, 3. So switch the place of all the x's and y's. This point stays the same. This point here becomes 1, -1. This point here becomes the point 2, 1. And then this point here becomes a point 3, 4. And you can see that it is a reflection across that line y equals x. Okay. I think that is our final page. So those are the types of questions you can expect to come out of Unit 1. So some of the key points here to remember then: finding the inverse of a function, both graphically. Question 5 here was finding the inverse graphically. If we go back and look, question 4 was finding the inverse algebraically by switching the place of x and y and solving for y. Okay. Question 3 was addressing transformations of functions, as was question 2. Question 2 was addressing transformations of parent functions. And question 1 is compute the difference quotient of a variety. So we've got a linear function here, we had a quadratic function. So go back if, and again, this has gone, it's been the same thing I've been preaching all semester. It may not be enough to feel fully prepared for the final exam if you can simply solve these questions on the review. What you need to ask yourself always is, am I comfortable and confident with the topic of, for example, the difference quotient? It's great if you can solve these two problems, but if this is on the final exam, the two problems are going to be different than this. They'll be the same type, maybe same level of rigor, but not these exact same questions. So make sure that you're not just feeling confident solving these problems on the review. Make sure you're feeling confident with the topic of inverses, transformations of functions, and difference quotient.